Okay, this is going to be the lesson video for Calc 3, section 14.5 on chain rule and implicit differentiation with multivariable functions. So let me go ahead and present the notes here, and we'll get started. Okay, so the chain rule. We'll start with what we know from way back when, even back in brief calculus. We learned the chain rule, and that was basically based on this idea of, in my mind, it's like unit analysis cancellation. So if you need to know what is dy dx, and y is a function of another function, which is x, in other words, a composite function where you have an inside function and then wrapped in an outside function, then you can take the derivative of the outside function times the derivative of the inside function, because dy du times du dx, the du's cancel, right? So there's sort of like unit analysis cancellation going on there, right? It enabled things like us to take derivatives of y equals e to the 3x squared, because we can find the inside function 3x squared here as u, and then rewrite the function as y equals e to the u. And then if we took the derivative of the inside function, du dx, that would be 6x. And if we took the derivative of the outside function, dy du, that would be e to the u, which is a copy. But when we resubstitute this back in, you get e to the 3x. And so then the overall derivative is the derivative of the outside times the derivative of this inside, the dy du dx part, right? So this is how we were able to extend all of our derivative shortcuts for more complicated structures. We take the outside derivative and then we multiply by the inside derivative. But what's going on behind the scenes is this chain rule idea. All right. So what we're going to do now is extend this idea for multivariable functions. The situation is a little bit more complex, but it's still based on this idea of unit analysis cancellation. There's many cases, right, but two main ones that show up. So the most simple case is if you have a function z, which is a function of two variables x, y, but then those two functions can each be written as functions of the same variable t, such as being parameterized. Z is a function of x, y, but x is a function of t and y is a function of t. Then the chain rule becomes that derivative of z with respect to t is equal to the partial derivative of z with respect to x times dx dt plus the partial derivative of z with respect to y times dy dt. And so you can sort of think of it this way, right? This is a small change. This is a small change in z, right? And it comes about because there's a small change in x and there's a small change in y. But these partial derivatives show how sensitive z is to changes in x. So it makes sense that you could take like the amount of change in x and then multiply it by how sensitive z is to changes in x to get the change in z that's produced by this change in x when I change t, right? And then also separately take, well, how much change in y is there for the change in t that I'm imposing, and then multiply that by something which is measuring how sensitive z is to changes in y, right? So the change in z comes about from a change in x when we change t and a change in y when we change t that are each scaled by how much those changes affect z. All right, so to keep it straight, we can draw a tree that helps us kind of remember this. So if we have z that we know is a function of x and y, and then x and y are each functions of t, then you could take derivatives or partial derivatives at each level. So since z has two functions that are, or two variables that are inputs, x and y, you could take the partial derivative of z with respect to x, partial derivative of z with respect to y, and then the full derivative of x with respect to t, because there's only one variable, and the full derivative of y with respect to t. And that means that to kind of remember this, if I have to go from this z to the t and it's in two spots, I'm going to have two kind of branches that I have to do. This times this plus this times this, right? Right, so let's actually do one. Let's say that I had z is defined as x squared times y plus 3x times y to the fourth, but then further y is parameterized as sine of 2t, and or x is sine of 2t and y is cosine of t. And I wanted to find dz dt at a particular time, right? So the first thing is I would say, okay, z is a function of x and y, right? So dz dt is going to be, first I have to say, how does z change with respect to x, then times how much x is changing when I change t, plus the amount of that z changes with changes in y times the amount y is changing when I change t, right? So that's just copying the formula. So let's fill in all these derivatives. The partial derivative of z with respect to x would be 2xy, right? And then let's see, this term here would be plus 3y squared, or 3y to the fourth, right? And then times the derivative of x with respect to t is going to be 2 cosine 2t, right? How did the little chain rule there, right? So derivative of sine is cosine, but the derivative of the inside is 2. And then I have to add on this, right? The partial, how much does z change with changes in y? So the partial derivative there would be x squared plus 12xy cubed, right? Taking the partial derivative of z with respect to y, and then multiply by how fast y is changing with changes in t, which would be negative sine of t. Okay, and then the whole thing we're going to evaluate when t is 0. So if I plug 0 in for t, well, first of all, if I plug 0 in for t, x becomes sine of 0, which is 0, and y would be cosine of 0, which is 1, right? So that means I'm going to plug 0 in for all x's and 1 for all y's. So I'm going to get 2 times 0 times 1 plus 3 times 1 to the fourth, and then that's going to be 2 times cosine of 2t, but t was 0, so cosine of 0, right? Plus, and then the x would be 0 squared plus 12 times 0 times 1 cubed times the negative sine of 0. Okay, and so continuing here, right, this is just going to be 0 plus 3 times 1 is 3, and then cosine of 1 is 1 times 2, right? And then this will be 0 and 0, so we end up getting 0 times 0. So the whole thing turns out to be 6, right? And that just means that if I do, like, for every 1 unit change in t, through all of its connections through x and y to z, 6 will change 6 units, or z will change 6 units per unit change in t. Okay? So that's application of the chain rule, first case, where you have a function that's a function of other functions, but those functions are each a function of a single variable t. All right, a little bit more complicated case, which we encounter. Sometimes we have z as a function of x and y, but then x and y are each functions of 2 parameters, s and t. And we'll see this more later in the next chapter when we do multiple integration. But graphically, this is showing that, z depends on x and y, right? But then x and y are each dependent upon 2 different variables, right? So all these derivatives would be partial, but that means that if you want to take the derivative of z with respect to s, let me change colors here, then that means we're going to go down the paths that lead to s. So we're going to have to take partial z partial x times partial x partial s, and then add on partial z partial y times partial y partial x, right? So if I wanted to find partial z partial s, the first thing I would do is take partial z partial x, which is, let's see, partial z. So the z partial derivative with respect to x would be 2xy, right, plus 3y to the fourth, right? And then the partial derivative of x with respect to s. So now we have a more complicated parameterization here. What's the partial derivative of this with respect to x? So that would be, let's see, this is all just a constant when I'm considering s as the variable. And so it's just a copy, and then this constant tags along for the ride, right? So that's this term, right? And then we would also have to say, well, what happens to z as I change y? So the partial derivative of z with respect to y is x squared plus 12xy cubed. And then how fast does y change with changes in x? So again, this is just a constant. And so we would have 3s squared times that constant, which is 2 cosine of t, right? And then you could plug in t equals 0 again. Let's do that actually. If we plugged in t equals 0, we would get, let's see, e to the s, and then this would be sine of 0, which is 0. And then this would be s cubed times cosine of 0. You know what? We would have to also be told something about s, or we can't find a point. So you know what? Rather than do this part, I'm just going to omit this. And let's just proceed to get the actual equations, right? You could always plug things in too, but you would have to be given a t as well as an s. I'm not sure why that didn't get copied over here. So let's do the partial derivative of z with respect to t. So for t, let me actually use a different color here. For this, right, we're going down this path, first to the x and then to t, and then to the y and then to t. So the partial derivative of z with respect to the t parameter is going to be first the partial derivative of z with respect to x, right, which is that same 2xy plus 3y to the fourth, but this time multiplied by how much x changes with changes in t. So we have to take the partial derivative of this structure with respect to t. Now the e to the s is a constant, and we're talking the derivative of the sign there. So that's going to be cosine 2t times the derivative of the inside, which is 2, right? And then same thing here, we would take partial z with respect to y, which is the same x squared plus 12xy to the cubed. But then we have to multiply by dy dt this time. So dy dt, this is a constant. Derivative of cosine is negative sine. Okay, and then you could plug x, y, or t and s all in there to completely evaluate if you had a particular place to evaluate that. So that's the main idea for chain rule, okay? And those two cases probably occur the most because often we have things where we have parametric forms where we have a single parameter t, or sometimes two parameters, s and t, or u and v, or something like that. But actually, this idea can be extended to any number of first-order level variables. So you could have, for example, let's say u is a function of x, y, and z, and then x, y, and z are each defined in terms of r, s, and t. So 3 variables at this level, and then 3 variables at the second level. And then if we wanted to find something like what's the derivative of u with respect to s, well, then you'd have to take first the derivative of u with respect to x, and then x to s, right? And then you'd have to add on the derivative of u with respect to y times derivative of y with respect to x, everything partial derivatives, and then everything with respect to u with respect to z times how fast z is changing with s. So this is extendable to any number of things. You can just make a little tree here to help you figure out what derivatives need to be included. Okay, so that's the first of the two concepts for today, the chain rule. The second idea is implicit differentiation, which we also have seen back in brief calculus and beyond there in Calc 1-2, it's covered as well. And so the idea is if you want to find, say, dy dx, and you have a function that relates x's and y's, right? But you don't want to have to pre-solve this for y first. It's either difficult or impossible to solve. Then you can just take the derivatives in place and then solve for the dy dx at the end after the derivatives have been taken. So you can take this structure and take the derivatives of every term. This particular one has two different functions. They're both functions, neither of them are constants because this is not partial derivatives, this is full derivatives. So each variable is a function. And that means we'd have to expand this with product rules. So you would have first times derivative of the second plus second times derivative of the first. But then when you get ready to take the derivatives, or you go ahead and take the derivatives, like the derivative of x cubed is 3x squared, and then no derivative here. But when you take this derivative, the derivative of y is 1, right? But because these letters don't match, you have to multiply by the derivative of the inside. Basically, what we're doing is we're saying, let me use this as an example here. So here we're taking the derivative with respect to x of y cubed, and that's going to be 3y squared, but then we have to multiply by dy dx. And that's because it's really not y cubed. Well, if we had x cubed and we were taking the derivative with respect to x, that would be 3x squared using the normal power rule shortcut, right? But if we have anything else cubed and we take the derivative with respect to x, the chain rule says it's 3 times that thing squared, but then times the derivative of that thing on the inside. All we're saying is if you have the inside as a y, then that means that you have to multiply by dy dx, right? So the reason we're multiplying by dy dx is it's just the chain rule extension. So the way you can kind of remember it is if these letters don't match, then that means you have to multiply by d this letter over this letter, right? And then at the end, you have an expression where you can algebraically solve for this term, right? Factor it out, get all the terms that don't have it on the right side, factor it out of the left side, and then divide to get this as dy dx. Right, so basically we're just saying if it's too hard to solve this algebraically for y, take the derivatives first and then solve algebraically for the derivative, right? Because it's usually easier, because in polynomials the derivatives are typically easier. Okay, so that's implicit differentiation as we knew it from even all the way back to brief calculus. But we can extend this idea more general if we use a slightly different form. So we'll rework this problem using this new form, and then I'll show you how it's extended. If instead you go ahead and take everything in the expression you're given and move it all to the left side and call it the function f, which is a function of, say, x and y equals 0, and that is implicitly defining a relationship between the variables, then you can apply the chain rule this way. If you take the derivative of this using the new chain rule definition that we've said, we have f, which is a function of x and y, right? Then I know that I can take the derivative of f with respect to x times dx dx plus the derivative of f with respect to y times dy dy, okay, or dy dx. Now, derivative of x over derivative of x is 1, right? So if you then solve this structure for dy dx, you end up getting that when you subtract this over, it becomes negative, and then you divide both sides by this term, you get dy dx is the negative of the partial derivative of f with respect to x over the partial derivative of f with respect to y. Kind of a weird thing that the full derivative dy dx is equal to the negative of the partial derivative of the function of everything brought to the left equals 0, but you swap the x here becomes on the top and the y here is on the bottom. Okay, so let's just use that exact technique to rework the problem that we could do the way we did back in brief calc, but using this new method that we're going to create a new function called capital F, which is everything brought to the left side so that it's equal to 0. So you just bring the 5 over, and then you take the partial derivative of that function with respect to each of the input variables. So fx would be 3x squared plus y, and then this is all constants, and then fy would be, that's a constant, so that would be x plus 3y squared constant. And then you just say that by this formula, dy dx is the negative of this partial derivative divided by this partial derivative, right? Which gets us to the same thing, because we just got on that other screen was this, which is exactly the same answer. Okay, so just another slightly more general way to think of it. And the neat thing about thinking about this way is we can extend this to more number of variables, higher number of variables. So let's say we had z as a function of x, y, and z, or yeah, z as a function of x, y, and z, and we want to express that as some function here. We want to find the partial derivative of z with respect to x by the chain rule, right? So if we have our generic function f, which is a function of 3 input variables, everything on the left equals 0, then the chain rule would say that this is df dx 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 plus df dy dy dx plus df dz dz dx, and that has to equal the derivative of 0, which is 0, right? We know that dx dx is 1, so this just becomes this, and this is actually equal to 0. There's a typo in the notes. It's really not because x and y are orthogonal, all the input variables are orthogonal. It's because while we are solving for partial derivative of z with respect to x, the partial derivative of z with respect to y, the partial derivative of y with respect to x is 0, because we're holding y constant, right? We're holding y constant when we're considering the derivative of z with respect to x. So while we're working on this, y is held constant, okay? And so this would go away, and you'd get a structure that's very much like the one we just did on the last screen. And when you solve it, you get that the partial derivative of z with respect to x turns out to be, I think there's a missing equal sign in here, equals. It ends up being negative the partial derivative of f with respect to x, and then the partial derivative of f with respect to z. So you take these letters and swap them. And similarly, if you want the partial derivative of z with respect to y, you end up swapping them, the partial derivative of y over the partial derivative of z of this new function where we've got everything to the left. So it's extendable to a different number of variables, okay? All right, and then there's one last thing that's in the notes. I'm just going to mention it briefly. When Miss Estu, last year when I was observing her teach it, she didn't talk about this at all. It's in the textbook. And she mentioned that it was in the textbook and said, read it if you're interested. If you're interested in this and you want to see the full treatment, I put some of it here in the notes. And I'm happy to make a PDF of some part of the textbook if you want. But basically, all these ideas are extendable to higher orders. So we've talked first about just the chain rule and implicit differentiation with first order derivatives, but you can do everything with second order derivatives. There's a couple of complications. And the main one is that when you take derivatives like this, you go through the process and you have to take a partial derivative with respect to r of a partial derivative of z with respect to x. Because there's more than one variable, this actually requires product rule and chain rule throughout. So it gets very complicated very quickly. And you can look at this example that I included in the notes from the textbook if you want. This is most of what the textbook covers. And ask me questions separately if you want it, but we're not going to do anything at all with higher order partial derivatives that would require the chain rule or implicit differentiation in this course. All right, so that should be enough to be able to cover homework problems for section 14.5. Give that a try, bring questions to tutoring or to class, and we'll see you at the next video.